Hi, I am your new Fern photon. Most people are familiar with electrons and electronics. Similarly, we photons enable a whole field called photonics, the science of light. I'm going to talk to you a little about light, optical fibers, and the development of optical fiber lasers. Photons can be portrayed as either particles or waves mathematically, but for our purposes, we will use a hybrid. Also, in my presentation, some technical terms will be in italics. This way, you'll know they might have external references. For instance, wavelength, represented by the lowercase Greek symbol lambda. In the optical spectrum, wavelength refers to the color of light. Blue is a shorter wavelength, around 400 nanometers, and red is a longer wavelength, around 700 nanometers. Light, of course, extends through a far greater spectrum than the human eye can see, from X-rays through to terahertz radiation. Most optical systems operate from the UV through to the infrared. Optical fibers became possible with the practical understanding of Snell's law. Light transitioning between transparent materials bends in proportion to the change in its velocity. Like a rod in a beaker appears bent at the air-water interface. The ratio of the velocity difference is the refractive index. In optics, we add materials called dopants into glass to change the refractive index. By putting two pieces of glass with different refractive indices adjacent to each other, we can emulate the bent rod effect. Imagine that a glass rod with a high refractive index core surrounded by a low refractive index cladding would guide light continuously down its axis. Well, that's exactly what happens. And we can also change the effective angle at which light is accepted by adjusting the refractive index of the two glasses. This is called the numerical aperture. High numerical aperture means broad angles of acceptance. If the core size is large so that multiple wavelengths of light or modes can enter by a variety of angles and can propagate down the core is considered to be multimoded. If the core size is small enough to only allow the passage of one wavelength at a specific injection angle, the core region is considered to be single mode. Depending on the size of the glass rod, the refractive index, and the wavelength, the core can be both single or multimoded. We strive for single mode. So, we generate certain wavelengths and use glass rods with diameters in the micrometers, less than 2 human hairs in diameter, small enough to be greatly flexible and resilient. Fibers. Fibers usually have one core and one cladding along with a protective coating. Most are made of quartz glass because of its purity. We use standardized nomenclature to specify the relative sizes of the core to the cladding. For example, 10-125 represents a single-mode fiber with a core of 10 micrometers in diameter and a cladding of 125 micrometers. A 105 micrometer core with a 125 micrometer cladding is represented by 105-125. Even though we know we can send light down a fiber, there are many variables that come into play. Fiber type, core size, numerical aperture, refractive index, and doping all contribute to expand the range and possibilities of light propagation. However, we strive for single mode, remember? Launching light down a single mode fiber is difficult and the light source is expensive. How can we strike a balance between power, efficiency, and economy? Through experimentation, it was discovered that changing the refractive index periodically along the length of the fiber could make the fiber reflect light. This creates a grating that takes advantage of Bragg's law to create a type of mirror. By changing the intensity and period of the grating, the amount of reflection for particular wavelengths can also be controlled. This quickly led to the development of a fiber laser. A fiber laser works by reflecting light through an optical cavity so that the stream of photons stimulates atoms that store and release light energy at useful wavelengths. On the periodic chart, these elements appear in the lanthanide series. Ytterbium is the most common lasing atom. Eli Schnitzer, a pioneer in optical fibers, learned to dope the core of an optical fiber with ytterbium to control the refractive index and photon absorption. Practically speaking, the ytterbium atoms have an absorption curve that looks like this. A broader spectrum of light can be absorbed at the shorter 915 nanometer wavelength, and a more efficient absorption can occur at the slightly longer but narrower 976 nanometer wavelength. The photon absorbed by the ytterbium dopant disappears, and electrons whizzing around the atomic nucleus move to higher orbitals on account of the absorbed energy. This process is called pumping to indicate that energy is being injected into and stored by the atoms in the fiber. Within about a millisecond, the electrons, otherwise unstimulated, drop to their original or ground state and emit a photon at a wavelength of 1064 nanometers. The energy efficiency of this absorption and re-emission is known as the quantum efficiency, and it is simply the ratio of the pump over the emission wavelength. It's impossible to get a higher optical efficiency than this number. With its close pump and lasing wavelengths, ytterbium can be made to lase with astounding optical efficiency. Pump, store, emit over and over again is a realistic oversimplification of the process. To maximize the coordination of the pumping and emission, an ingenious fiber optical cavity, sometimes called a resonator, is constructed. At the pump end of the cavity, a high reflector made using a fiber Bragg grating is spliced to a fiber that is doped with ytterbium atoms. At the output end, a similar fiber Bragg grating with a modest reflectivity of around 10% is installed. Thus, a very simple monolithic single-mode laser device is created. Monolithic in fiber terminology means that once the light is in the fiber, it stays in the fiber, end to end. However, the length of the doped fiber is important as it determines how much of the pump light is absorbed. We use the term absorption length for the combination of length with the amount of doping. Typically, a fiber laser has an absorption length of about 95% of the pump energy. This is to avoid having a section of unpumped fiber in the laser cavity. An unpumped section inevitably charges itself and self-lases, resulting in a failed fiber. To pump this device, an optical laser diode can be installed on the pump end. Because such a laser is single-mode, its power is limited to the output of a single-mode pump diode times the quantum efficiency of the laser. Single-mode pump diodes are expensive and relatively low-powered. To achieve higher power, either more pumps need to get connected to a fiber, or the fiber will need to get much fatter. In fact, over time, both came to be. It was discovered that light, once guided by the core, continues to propagate for a significant distance even when the core is tapered until it is essentially gone. The light can then be recaptured by a new core that intersects the light path. This path is called the evanescent field. By extending this concept, it was discovered that multiple fibers can feed into or split out of one evanescent field, leading to the development of a fused biconic coupler. There are limits to this phenomenon, however. The brightness, defined by the core area multiplied by the numerical aperture, must be conserved. For example, a coupler can be made with two input fibers of a 100 micrometer core diameter and a numerical aperture of 0.12, and an output of 100 micrometers with a numerical aperture of 0.24. If we now change our laser by adding the newfound coupler to the front end, we can see that the laser power can be doubled. Unfortunately, practical limits quickly set in when we try to add a third diode for a tripling effect, since each input would require a pump diode with a very small numerical aperture and ultra-high brightness. These diodes have a matching ultra-high price, not practical at all. More economical high-power pump diodes have a larger numerical aperture and a larger diameter output fiber. Using these economical pumps requires the use of double-clad fibers. The invention of double-clad fibers enabled very high-power fiber lasers with good manufacturing economy, great electrical efficiency, and astoundingly high brightness. In principle, a double-clad laser fiber works the same way as the conventional fiber we just described. However, the double-clad fiber is larger in diameter and has a second pump cladding with a very high numerical aperture. Now, even conserving brightness, this will allow a coupler with 6 legs at 0.22 numerical aperture each. Pumps of up to 600 watts per leg are commercially and competitively available for this coupler. This is encouraging. Once the laser is assembled as before and we apply pump power to the diodes, we quickly see that much of the pump light simply passes down the cladding without intersecting successfully with a dopant ion in the core. Without this intersection and transfer of power, the laser cannot work. The solution to this problem is to create extra reflecting facets on the outside of the first cladding. Schnitzer, remember him? Found that changing the shape causes enough redistribution of the light in the cladding to force a high level of interaction with the core. Now we have created another situation, too much light. As power in the laser goes up beyond a few hundred watts, photons in the core start to behave differently, much like surging traffic on a congested highway. Nonlinear effects start to appear, such as Brillouin scattering and Raman scattering. The solution is the same as on a highway. We add more lanes. For fiber, it means increasing the diameter of the core. This obviously reduces the light intensity quickly because the core area increases with the square of the radius, so a doubling of the diameter quadruples the light carrying capacity. And with this increase of core diameter comes the loss of the single-mode beam quality that makes fiber lasers so effective. What to do? We've determined that the acceptance angle in the fiber is dependent on the refractive index difference between the core and the cladding. Dov Kleiner and Jeff Koplow found that bending the fiber also affects how the core accepts light. They also recognized that the single mode, or the fundamental mode, propagates down the fiber with a slightly lower numerical aperture than any of the higher modes. The combination of a low numerical aperture in the core and a bend in the fiber allow the higher modes to escape, leaving the fundamental mode in the core. The evanescent field of the single-mode beam expands to fill the core diameter, avoiding nonlinear effects. Best of all, the amount of energy from the core that escapes as a higher mode is minimal. Serious, extremely high beam quality fiber lasers were now possible. Laser technology has evolved over the past half-century. The power to cut and weld and do amazing things with directed energy has spread to all parts of the globe. Many refinements are still being developed. Advances have also been made in using laser fibers for specialized telecommunications, scientific, industrial, and directed energy applications. Lower power diodes can create and manipulate seed signals, often as pulses. However, the signal can attenuate over distance, which requires amplification. To do this, we need to modify our 6-to-1 coupler into a 6+1-to-1 coupler and send a seed signal directly into the core of the fiber. With this configuration, we can eliminate the Bragg reflectors and simply stimulate the laser emission with a seed signal of our choice, an avalanche rather than a resonance effect. However, realize that a residual pump power totaling about 5% is quite significant with a fiber laser operating at 1 or more kilowatts. This valueless power could cause all manner of safety and engineering problems in beam delivery systems. So, additional components such as residual pump strippers are added to the very output end of the fiber. The stripper has a higher refractive index than the nominal cladding on the fiber. This then catches the high numerical aperture light remaining from the pump and releases it out of the fiber as lost thermal energy. Further refinements such as sophisticated electronic feedback and control mechanisms are still in development. So you see, creating a viable high-powered laser is a result of intense research and finely tuned techniques. We sincerely hope that this introduction was useful and informative. For more information, the parts to build your own laser, an educational kit, or one of our many complete industrial, scientific, or defense-oriented lasers, please give us a call or find us on the web. Cheers!